Hi, thank you for attending today's interesting webinar, where we will be covering the topics that you can see in this slide. First, we are going to learn about massive MIMO beamforming technology and why it is important in today's 5G networks. Then, we will be sharing the gaps in the current test specifications and the solutions provided by Keysight for closing these gaps. Finally, we will have a real demo of massive MIMO beamforming verification and analysis. My name is Rafael Garcia, and I am Keysight Wireless Analysis Go-to-Market Lead. The other presenters in this webinar are Jukka Kirolainen, Pertti Kangas, and Subin Narayanan, experts from Keysight's channel emulation solutions. Jukka, over to you.
Thank you, Rafa. Now I'm going to tell you about the basics of MIMO and massive MIMO, and about the benefits of massive MIMO, and some high-level description on how it works. So starting from very basics to understand what is MIMO. Single antenna transmission suffers from fading due to the multipath propagation. That can be mitigated by MIMO. MIMO transmit diversity can be used to transmit redundant copies of the data to improve the reliability of the link. Phase diversity can be utilized by transmitting the data via multiple non-correlated propagation paths. This can be enabled, for example, by forming beams into different directions as shown here. Then spatial multiplexing is a method to increase the data rate by transmitting parallel data streams in spatial domain instead of repeating the same data. Thus, both of these methods and combination of these can be actually used to utilize the richness of multipath propagation channel to improve the link quality and throughput. The parallel data streams are called as MIMO layers. The MIMO precoding or beamforming capability with traditional MIMO with low number of antenna ports is quite limited due to the limited channel state awareness and adaptation capability with fixed or limited set of precoding options with open loop or closed loop methods. So what is the difference between MIMO and massive MIMO? Massive MIMO enables better utilization of multipath propagation environment by improved adaptation capability with much better beamforming resolution. It can enable higher number of layers and enhanced reliability. So, how to define massive MIMO? Obviously, massive MIMO means high number of antennas from tens to hundreds to enable good resolution for beamforming. It means slightly different things for FR1 and FR2 in practice. FR1 is about digital beamforming with high number of logical digital baseband controllable antenna ports that enables flexible MIMO precoding and scheduling procedures at FR1. FR2 is implemented with analog beamforming and low number of logical antenna ports for MIMO. It is more focused on compensating high path loss by beamforming than increasing the capacity by increasing the number of spatial streams. Analog beamforming with typically fixed beam grids leads into complex beam management procedures via the TCI states. For the rest of the presentation, we focus mainly on FR1. Then about the benefits of massive MIMO and benefits of increasing the number of antenna elements. Obviously, the first benefit is the increased power level at the receiver. By adding the number of antenna elements, we get 3 dB additional gain always when doubling the number of antenna elements. The second benefit is the MIMO capacity. By enabling narrower beams, better resolution to distinguish between the multipath propagation components of the channel model to enable higher number of multiple independent parallel data streams for one UE. And obviously, for the multi-user case, it enables co-scheduling of multiple UEs with the better resolution, better capability to achieve good isolation between the UEs in the multipath propagation channel. Then about how massive MIMO beamforming works in practice. In 5G NR, everything is typically beamformed. This obvious difference to 4G. There is different beamforming applied for different reference signals and physical channels. Broadcast channel SSBs are transmitted on wide beams, and channel state information reference signals are typically also beamformed with wide beams in FR1 case. The data channel PDSCH, which is most interesting and relevant for the link performance evaluation, uses UE-specific and actually MIMO layer-specific narrow beams. This requires accurate spatial channel information and adaptation for precoding. Downlink spatial channel information knowledge is essential for the base station to apply optimal beamforming weights. There are two alternative concepts for acquiring the spatial channel information. First is UE feedback-based method according to the UE channel estimation of downlink CSI areas. UE estimates the MIMO channel matrix for CSI areas antenna ports, determines the optimal precoding matrix among the predefined set of precoding matrices, and reports the corresponding PMI parameters to the base station. Second method is based on base station uplink channel estimation for UE transmitted sounding reference signal SRS. Base station can determine the optimal downlink precoding weights according to the uplink channel estimates because the downlink channel model is reciprocal to uplink. This obviously applies only for TDD operation and is valid only if the delay between the uplink measurement and downlink transmission is not long compared to the channel coherence time. Aging of the channel estimate is one of the testing aspects. Realistic spatial channel models, channel emulation. Accurate channel information enables sophisticated precoding methods, such as different variants of zero forcing. And some further details about the CSIR's port configurations, CSIR's beamforming, and PMI feedback concept on the couple of next slides. The details for all of these are defined in ES38.214. The options for number of CSIR's antenna ports range from 4 to 32, but the number of antennas can be much higher, as explained in the following slides. As even, for example, 8 CSIR's antenna ports can be used by the massive MIMO base station. This table snippet from the spec is for Type 1 codebook, but similar options are available also for Type 2 codebook. The example here shows 16 CSIR's antenna port case with N1 equal to 4 and N2 equal to 2. N1 defines the number of antenna elements in horizontal domain, meaning the number of columns of the antenna array, and N2 defines the number of vertical domain antenna elements, meaning the number of rows in the antenna array. So there is a planar array with 8 elements in this case. When adding the polarization, we get 16 antenna ports altogether, 8 for both polarizations. This is how the ports are defined, but even with low number of CSIRS antenna ports, we can have a high number of antenna ports for digital beamforming by combining multiple elements into one CSIRS antenna port. In this case, the CSIRS of each CSIRS antenna port is beamformed. Here is a similar example with 16 CSIRS antenna ports and 2x2 antenna elements for CSIRS beamforming. In addition, each antenna port within CSIRS antenna port can consist of a fixed subarray of 2 or typically 3 vertical elements combined for a fixed beamforming. So this is a similar example as the previous slide 16 CSIRS antenna ports with 2x2 subpanel antenna array for digital beamforming, but in addition we have those fixed subarrays which are used for fixed analog beamforming to increase the array aperture in vertical domain and to narrow the elevation domain beam and enable obviously higher gain for the beamforming. In this case, each CSIRS antenna port consists of 2x2 planar array having the 2-element dual polarized subarrays as the radiating element in the array. And these 2x2 planar arrays can be used for the digital beamforming for CSIRS beams. So the CSIRS transmission can be either beamformed or non-beamformed. Here on the left side, we have an example without CSIRS beamforming, and this obviously enables a high number of CSIRS antenna ports for the PMI adaptation. In this case, the base station transmits a single CSIRS set over the 32 antenna ports, and UE reports the rank indicator and PMI for the 32 port configuration. So for example, if the UE has 4 antennas, it will estimate 32 by 4 channel matrix and determine the PMI based on that. On the right side, we have the example with the beamformed CSIRS. And in this example, the base station is using 2x2 subpanel antenna array to form the CSIRS beams for each of the CSIRS antenna ports. And here, for example, we saw 3 beams. In practice, there can be higher number of CSIRS beams transmitted by the base station. Here, one CSIRS resource set is transmitted on one beam. So each CSIRS antenna port transmits the same CSIRS resource set with a similar beam. So UE sees 8 CSIRS antenna ports with the specific CSIRS beam as a kind of radiating element of the 8 port antenna array. Based on the different CSIRS beams, the UE determines the best CSIRS beam and reports the CRI and rank indicator and PMI information for the base station for this 8-port configuration. So in this case, for example, if the UE would have 4 antennas, it would estimate the 8x4 channel matrix and determine the PMI based on that for the 8-port base station antenna array. And some further details about the PMI feedback and the PMI-based precoding matrix calculation. The UE is configured by the basic antenna topology parameters, number of elements in horizontal domain, number of elements in vertical domain, codebook type and codebook mode, and number of panels at the base station. The UE determines the optimal precoding matrix based on the specified set of options, and reports back to the base station the PMI parameters I11, I12, I13, and I2. These 4 parameters together with the antenna array geometry define the resulting beams with the chosen precoding matrix. Actually, the resulting precoding matrix is a vector of beam weights for each MIMO layer. So if we look at the precoding matrix, the number of columns is the number of layers, and the number of rows is the number of antenna ports in the precoding matrix. And typically there are 2 overlapping beams for the polarizations. So, for example, in a 4-layer case, we can see 2 different beam shapes, both having 2 polarizations. So, if we look at the examples here, for example, the PMI 0000 for antenna configuration with 8 horizontal elements, and a 4-layer case, we can see clearly two different beam shapes here. So here, for example, we can consider the blue beam to deliver layers 0 and 2 over the 2 orthogonal polarizations, and red beam shape to deliver layers 1 and 3 over the 2 polarizations. The red beam is kind of distributed into 2 lobes and having a null in the beam direction of the blue beam. Obviously, the PMI optimal PMI selection depends strongly on the multipath propagation between the base station and UE. The PMI selection must be well adapted to the cluster directions of the propagation channel, and this is obviously one of the important testing aspects, also with channel emulation and with realistic spatial channel models. Here is an overview of the SRS-based operation. The UE transmits the SRS in uplink, and base station determines the optimal beamforming weights based on the estimated uplink channel matrix. This enables flexible downlink beamforming methods, such as different variants of zero forcing. Now handing over for Pertti, who will tell more about testing of massive MIMO.
Thanks, Jukka. Hello everybody, my name is Pertti Kangas and I'm working in Keysight Proxim Channel Emulator product management team as a product manager having responsibility of base station testing solution. How to verify massive MIMO performance thoroughly in all conditions. Testing in the laboratory is more efficient than in field. In the laboratory, we have wide control over different variables and the availability of better tools and equipment. Also, test repeating are easier in the laboratory than in the field. Product testing needs to be done for all new software releases and under various network conditions: city center, shopping malls, high-speed moving vehicles, etc. Product testing phases are divided in development, acceptance, interoperability, and field deployment. It is important to validate interoperability and performance of real devices and massive MIMO base station in each of these phases. Development phase testing is focusing on uplink and downlink beam testing with the real UEs with the 24/7 continuous integration testing. In acceptance and interoperability phase, testing focus is in performance, network interoperability, and field trials, where focus is in latencies, call success rates, and data throughput testing. In deployment phase, testing is focusing on new release lab validation and network optimization testing, as well as the field issue debugging in the laboratory environment with proper tools. And let's look how standardization bodies are defined massive MIMO testing. 3GPP specification defines how to verify transmit signals quality for single-layer RX demodulation capability under fading condition. It doesn't define how to verify MIMO, massive MIMO beamforming, nor multi-user MIMO fading condition testing. ORAN test specification additionally define how to verify radio unit interoperability with the distribution unit. Even Open RAN specification includes beamforming and multi-user MIMO test. Those purposes are to validate the interoperability of ORAN system components, not the massive MIMO fading performance testing. Massive MIMO performance are not tested under any conformance test specification. So, what we can offer to massive MIMO testing? We have fully integrated turnkey testing solution for massive MIMO base station. It is optimal testing solution for unidirectional 5G FR1, 16TR, 32TR, and 64TR massive MIMO base station testing. It is verified turnkey solution including all instrumentation, software, test cases, and test scenarios. It will accelerate 5G MIMO base station market launches, and with exceptional RF linearity performance, it supports 256 or 1024 QAM testing with the repeatable results. With our solution, you are able to test your implementation with field condition in the laboratory before you start field deployments. And our solution is supporting Keysight analytics tools for in-depth troubleshooting, benchmarking, and analytics. And tools are like ESA, wave judge, and device analytics. tools for automated testing and customer test case creation. Performance Test Manager application is the software providing comprehensive suite for the fully automated end-to-end laboratory testing with KPI and test reports. It controls equipment, UE, and channel condition created by PropSim during the test runs. It executed ready-made or user-defined test cases and scripts. PropSim Standard Tools is a graphical user interface of PropSim providing access to included standard channel models. GCM Channel Studio software is including tools that enables creating customer-specific channel models. Dynamic modeling capabilities includes mobile speed, multipath profile, range delay, and base station antenna correlation. The PropSim GCM Channel Studio tool is an industry-leading channel modeling tool. It should support user-defined 3D spatial scenarios and dynamic modeling of movement, arbitrary and complex test scenarios, massive MIMO test scenarios, customer-owned antenna beam pattern model embedding, and it supports different standard channel models. For replicating field-measured scenario in the lab, we have our Field-to-Lab tool. This tool uses data captured in the field to build tests that replay wanted test route. It enables repeatable testing real-world field conditions in the laboratory environment with the debugging tools. With RF scanners and real UEs, we collect real-world RF conditions, and with our Field-to-Lab Converter tool, we create test cases and channel models that will be run in PropSim. S8803A Massive MIMO Fading Performance toolset includes also ready-made test cases and test scenarios. In this slide are examples of data throughput test scenarios, beam management, link adaptation, data performance, and latency test scenarios, as well as mobility test scenarios. PropSim Channel Emulator-based solutions support efficient tools for analytics and debugging for phase and time-coherent massive MIMO measurement. With the VSA 89600 software, RF and RxTX beam measurements with the wavejudge, accurate and coherent layer 1 to layer 3 stack analysis, and with Signal Studio, you can program uplink waveform insertion, for example, interference profiles.
Thank you, Pertti. We are all aware that the channel effects must be seriously considered in radio communication systems. The channel can have negative impact, but it is also possible to take advantage of the imperfections, as it is the case of MIMO. As we saw, PropSim can simulate the channel conditions, and we can repeat the testing in the laboratory as much as we want. PropSim can also capture the traffic between the UE and the base station, and here is where WaveJudge Wireless Analyzer is the perfect match, because it can import those captures and perform an advanced physical and protocol correlation. This way, we can get visibility into the real 5G stack and eliminate multi-vendor discrepancies, because it follows 3GPP official specifications. Combining PropSim and WaveJudge has a strong value proposition because it is just a software add-on, which means that we have a reduced cost and we don't need to change any hardware setup in the lab. The great advantage is the focus and the optimization in the testing workflow, because WaveJudge will provide an intuitive, quick, and effective error guidance. Now, my colleague Subin will provide a detailed demo of the combination of PropSim and WaveJudge.
In this demo, we will be focusing on the beam alignment analysis or the verification in a massive MIMO setup. For that, we consider the two use cases. The first one is the static UE, where the UE direction is modeled at minus 7.25 degree, and the second one is the dynamic UE, where you can see here that UE is moving along the path as shown here, and it's a pure line of sight model. And here we took the signal capture at the direction 0, -2, -4, and -6 degrees. And in both use cases, we consider the single layer transmission. Here is a block diagram of our lab setup. We have a 64-port G-Node B at our lab, and it's dual polarized, and each polarization is connected to one PropSim, and that is one polarization is connected to one PropSim, and the second polarization is connected to the second PropSim, and there are 32 ports per PropSim. And at the output, we combine the output ports of each PropSim using a combiner and feed that to the UE, and it's a NSA operation. That is why the G-Node B is also connected to the UE. And as shown here, the PropSim supports the signal capture both at the downlink ports and also at the uplink ports. And what WaveJudge does is that it actually takes this captured IQ data, and we feed that to the WaveJudge software, and the WaveJudge gives the more in-depth analysis of the physical layer and the higher protocol information of the captured data. And here is the actual lab setup. You can see here a G-Node B, you can see here a 5G UE, and the two PropSims. And the G-Node B in this setup actually supports the PMI feedback-based beam alignment, and it supports 8 CSIRS antenna ports, and the codebook configuration N1, N2 is 22 as given here. The PropSim signal capturing settings are shown here. As shown here, a user can actually select which are the ports to be captured just by clicking on the corresponding ports, and user can also specify the capture duration. As shown here, it's like a 500 millisecond here, and that is the basic signal capturing functionality in the PropSim. And for this demo, for the simplification, we capture the signal for the single polarization as shown here. So we capture only from the 32 ports at the one PropSim input and the output, and we use this particular IQ data for the further analysis in the WaveJudge. Our automation software called Performance Test Manager actually enables the triggering of the IQ data. What I mean by triggering is that it defines the time instant from which onwards we want to capture the IQ data. This is done by defining a delay parameter in the PTM. So here it is the 11 second. What does it mean is that 11 seconds after starting the emulation, the PropSim will start capturing the IQ data. So that's the PTM software, and the next few slides we will be showing the video recording from our lab. Once we open the emulation, go to the signal capture and define the IQ data capture format. Actually, the WaveJudge request is to be in the STF format, and after that give the any name for the STF file. Then we will go to the enable capture the ports which are to be captured just by ticking on it. Here we have to capture from all the 32 downlink ports and one uplink ports, as we are doing it here now. And also we can specify the capture duration here just by length of the capture length, then click the start button. And in the PTM we had to first choose the test case, and here I am choosing the correct test case here. And once I have done that one, just check the test case name and click the run. So now a dialog box will open. It shows all the dialogues from the PropSim, whether the PropSim emulation is started or not, and we can also monitor the progress here. Here you can see that the RSRP measurements are going on. That means the setup is ready and the IQ data capture has been started at the specified time. So first we go in terms of port configuration. For that we had to go to this configure test, and here we had to mention which is the technology we are using. Here we are using the 5G NR. So you can add which are the technology using by adding the cell. Here it's 3GPP LTE cell is there and 5G NR cell is there. In this NSA configuration, we are focusing on the NR part. So we added only the 5G NR part, and after that we can add downlink and uplink ports just by going here, clicking here downlink and uplink ports, and then we should mention under the downlink ports how many downlink ports are there and how many uplink ports are there. So as we mentioned before, we are focusing on the 32/1 configuration, that is 32 downlink ports and 1 uplink ports, single layer transmission. So basically to add various ports, we have to go to in the downlink session, we go to the downlink section and go to this add RX port. So basically by clicking the RX port, we can add all these RF ports. So like this one, we have created this configuration of the antenna array or the RF ports. Once we have done this one, the next task would be to inform WaveJudge about how the cell is configured. For that, we had to go to the import functionality. So first it is the file, and here is the import functionality and import other capture format, and there is a Keysight PropSim. And in the import functionality, we are doing two functionalities. First is to import the STF file or the PropSim IQ capture, and second one is we are configuring the WaveJudge with the cell configuration parameters. So as we mentioned before, PropSim actually supports two types of capture, like all the ports in a single file, or all the RF ports are captured in the separate STF files. In this example, we have actually chosen the second option. We can do it with the first option also, but we just chose the second option. And next we had to give the WaveJudge about the information on the cell configuration. So we know that it's a 5G NR test mode. We should give whether it's a NSA or SA mode. The reason why we had to choose this is SA or NSA mode is that the information we are giving to configure the SA mode and NSA mode are different. For the NSA mode, to give the information on the cell configuration to the WaveJudge, only RRC reconfiguration message is required. For that is RRC reconfiguration message actually contains all the cell configuration information, and we had to give the hex string of this RRC reconfiguration message to WaveJudge. From this hex string, the WaveJudge intelligence will extract all the cell configuration information, all the upper layer information, all the high layer protocol, and all the cell information the WaveJudge will extract. For the SA mode, we had to give the hex string of the SIB1 and RRC connection setup message. Since it is an NSA mode, we have to give the hex string of the RRC reconfiguration message, which I have already saved here in my PC. For example, this is RRC string saved in the TXT format. So I just had to open it. So once I click the import function later on, the WaveJudge will extract the information on the cell configuration from this hex string. That's about the cell configuration. Next is to import the captured IQ files. For that, we had to go to this browse function, and for example, here is my captures here. So I can go here. As I mentioned that I have total 33 ports, 32 ports in the downlink and 1 port in the uplink. Here it's like that's all order actually. This is in the 0 degree. For example, I have the captures for the other direction as well. You can see here is a 2 degrees there. So basically I have captured in a multiple direction. To import, actually what we had to do is that select all the ports we want to import. For here it's like 32 downlink and 1 uplink. Up to this one I had chosen everything, and open it and press the import function. Once it is once we click the import function, the wave judge will start processing the data based on the given hex string and the given data. So I'm not pressing the import here because it will take a couple of minutes to process. So I have already processed a file from the same setup. It's here. So once the wave judge process the data, you will see a GUI like this one. Here you can see all the information, all the uplink and downlink messages, PDCCH, PDSCH, PUCCH, UCI, PUSCH, all the information you can see here. Just by clicking on this PDCCH, you can see here what is the beamforming phase for subcarrier and how's the power per subcarrier. You can see the constellation diagram, for example, by clicking the PDSCH and the PDCCH. Also, you can see what is the constellation diagram, and here is a prop sim IQ data source information, like which port is collected from the which SDF file. This information also we can find it here. So, for example, if you consider the PDCCH, the DCI format 1.1 contains the control information to configure the downlink channel. For example, here you can see that you can see all the information in the DCI format 1.1, and also you can see the DCI format 0.1, actually, which is to configure the uplink. So basically, if you consider this particular PDCCH, it contains both the DCI format 1.1 and 0.1, which is to configure the PUSCH and the PDSCH. So if we click on this one, PDSCH, the downlink data, we can see here what is the DMRS power per the DMRS. You can see that it shows only one DMRS port. That means it's a single layer transmission. So this information we can find it here. What is the EVM? What is the frequency offset? All this information we can see here. And also all the other information like the PDCH, what is a code word, what is a VRB to PRV interleaver, or what is the start of the bandwidth part, DMRS information and DMRS configuration type, DMRS position, all the information, all the higher layer information and the physical layer information also we can find it here. Moreover, we can see here all the lot of results functions here. For example, there is in the time domain, there is all these functions are available. That is the MIMO channel per subcarrier, IQ data, EVM per symbol. In the frequency domain, we can see what is EVM per subcarrier, spectral power, MIMO channel, and also the beamforming phase per subcarrier. So actually, we can also import this function just by going the chart data and just save it in the CSV format. For our later part of this presentation, we have used this exported data to plot the beam based on the based on this phase and the amplitude of the PDSCH. So that is about the downlink, and also we can check how the UE is reporting based on the how the UE is reporting the PMI. For that one, we can just go here. For example, there's a lot of message to filter out the UCI. You can just go to chart properties here and choose only the UCI. So once we have this UCI, you can just click on the UCI, for example, this one, and you can see here what is the CSI reports. Actually, it's a rank 1, so layer 1, for example, and you can see what is the PMI reported. It's I11 is equal to 3, I12 is equal to 1, and I2 is equal to 3. So this is the PMI. It is reported by the UE. So you can see that there is some vertical scanning, and the reported PMI I11 is corresponding to the horizontal scanning, and there is a subband properties also informed in terms of I2. Based on the exported PDSCH beam weights from the wavejudge, we have created this beam, PDSCH beam, and also based on the PMI values, we have created this PMI beams. As you can see here, from the PDSCH beam, it is focused that or aligned at the -7 degrees in the azimuth plane, and which is closely matching with the static UV case where the UV direction is at the -7.25 degree. Now we compare this beam with the PMI beams. In the PMI, we can see multiple beams, and also there is one beam at the -5.75. The reason for this multiple beams is like how to say the number of CSI RS ports are less than the actual number of antenna ports. Like actual number of antenna ports are 32 and the CSIRS ports are 8. Because of this one, the CSIRS ports are multiple lambda space, that's like 4 lambda space, and that's the reason for this multiple lobes. And what happens is that the CSIRS beam filters out this all the unnecessary side lobes and keeps only the required main lobe at the -5.75. We don't find an exact match for the -7.25 degree. This is because of the granularity of the PMI beams are like 2 degree. So as you can see here that that's the reason why we have this small mismatch. Now we continue the analysis in the dynamic UV, and we are focusing on the UV direction at the -4 degree, and we follow the same approach. We exported the PDSCH beam weights, and also we identify the reported PMI, and the reported PMI for this -4 degree case is like I11 is equal to 2, and I12 is 1, and I2 is 3. And we can observe that the PDCH beam from the exported weights are focusing at the -4.2, which is closely aligned with the UV direction. And also from the theoretical PMI beams, we see that we see there is a main beam at the -3.75. So in this particular measurement, we found a close match for all the beams. For the further verification, we verified the beam at the 0 degree, and we follow the same approach. We exported the PDSCH beam weights and the reported PMI values. And the analysis shows that the PDCH beam is pointed at the 1 degree, and the corresponding UV direction is like the 0 degree. So there is a small mismatch in the direction, and the corresponding PMI beam, the theoretical PMI beam is at the 1.75 degree. This is because of the PMI beam granularity. And we can also observe a very interesting fact here. Here the side lobes in the elevation planes are a bit stronger. This is because the one RF port actually consists of multiple stacked antenna elements, and this antenna element pattern actually eliminates the strong side lobes in the elevation plane. So that and then in reality we don't have this strong elevation plane side lobes. So that's it from the demo, and in short we have shown the powerful combination of the prop sim and the wavejudge in analyzing and verifying the massive MIMO beamforming capability.
Okay, and we have reached the end of this webinar. I will close it with a very quick summary with images that I am sure will help you to remember. We started with a great overview and details of massive MIMO beamforming technology and why do we need it. Then we provided details of testing and verification solutions that cover the gaps in existing official test specifications. And finally, we could enjoy a demo of the combination of Keysight PropSim and wavejudge that help us to identify if all the signals and protocols involved in massive MIMO beamforming are correct, and otherwise effectively troubleshoot the root cause of any issues. Thank you very much for attending, and we hope that you have enjoyed it.